Could an asteroid actually end us? Somewhere out there right now, a piece of rock the size of a small building is moving through the darkness of space on a path nobody has fully mapped. It is not glowing. It is not blinking. It is not sending out any signal to announce itself. In most cases, we don't even know it exists. That is the exact question behind NASA's Planetary Defense Program, and here is the part the headlines are not telling you. This is not just a story about ancient extinction events and Hollywood disaster movies. It is a live, ongoing operation happening right now in 2026, with a spacecraft already redirected, a telescope racing toward a 2027 launch, and a date already locked into the calendar in 2029 that will bring an asteroid closer to Earth than some of our own satellites. Right now, scientists estimate that more than half of the asteroids large enough to flatten a city have never been found, tracked, or ruled out as a threat. Not because nobody is looking, because the sky is bigger than our ability to watch it. Stay with me, because by the time this is over, you will never look at a clear night sky the same way again. I am Your Name John, and this is your channel Nebulix. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to the beginning. To understand why NASA takes this seriously enough to run an entire coordination office dedicated to it, you have to go back 66 million years to a morning that no human witnessed and no human could have survived. An object roughly 10 to 15 kilometers wide, moving at somewhere close to 20 kilometers per second, struck the coast of what is now Mexico's Yucatan Peninsula. The energy released was not measured in tons of TNT because the scale of tons stopped being a useful unit. It was measured in billions of times the energy of the atomic bombs dropped in the 20th century combined. The impact carved a crater more than 150 kilometers wide. It ignited wildfires across entire continents. It threw enough dust and sulfur into the atmosphere to blot out the sun for years, collapsing the plant life that the entire food chain depended on. Roughly 3/4 of all species on Earth, including every non-avian dinosaur, went extinct. Now, here's the detail that turns this from ancient history into a live, ongoing question. That impact was not a freak, one-time cosmic accident that happened once and will never happen again. It was simply the largest known example of something that happens on a spectrum constantly, at every scale, all the time. In 1908, a much smaller object, likely no more than 6 diameters across, exploded in the atmosphere above a remote stretch of Siberian forest near the Tunguska River. It never reached the ground. It didn't need to. The shockwave from the airburst flattened an estimated 80 million trees across roughly 2,000 square kilometers, an area larger than some countries. Had that object arrived a few hours later, given the rotation of the Earth, it would have detonated over St. Petersburg instead of an empty forest. In 2013, an object about 20 meters wide, smaller than the one that caused Tunguska, entered the atmosphere over Chelyabinsk, Russia. Nobody saw it coming. Not one telescope on Earth detected it before it arrived, because it approached from the direction of the sun, where our instruments are effectively blind. It exploded with the force of roughly 30 Hiroshima bombs, injuring around 1,500 people, mostly from flying glass as shockwaves shattered windows across the city. That object was completely undetected until the moment it lit up the sky. Sit with that for a second. In the 21st century, with satellites, radar, and some of the most advanced telescopes in human history, an object capable of injuring over 1,000 people arrived with zero warning. That is the exact gap NASA's Planetary Defense Coordination Office exists to close. Here is how to picture the actual defense system currently protecting Earth, because it is not what most people imagine. There is no laser cannon. There is no missile silo built for asteroids. What exists instead is something quieter, slower, and in its own way more remarkable. A global network of telescopes, mathematicians, and orbital physicists whose entire job is to look up, calculate, and count. At the center of it sits an organization called CNEOS, the Center for Near-Earth Object Studies, based at NASA's Jet Propulsion Laboratory. Every time a telescope anywhere in the world spots a moving point of light that might be an asteroid, that observation gets funneled into a global clearinghouse called the Minor Planet Center. From there, CNEOS calculates the object's orbit and runs it against a monitoring system called Sentry, which continuously checks whether that orbit brings the object anywhere near Earth, for decades into the future. The threshold that matters most is 140 meters. Objects at or above that size are large enough to devastate an entire region, not just a city block, and they are the ones Congress specifically directed NASA to find. In 2005, lawmakers passed what's known as the George E. Brown Survey Act, setting a goal: find 90% of all near-Earth objects 140 meters or larger by the year 2020. That deadline came and went. NASA did not hit it. As of now, scientists estimate we have found less than half of those objects. Somewhere out there, more asteroids capable of leveling a region than we have ever cataloged are still moving through the dark, completely unknown to anyone. This is not a failure of effort. It is a failure of tools. Ground-based telescopes, no matter how good, are fighting physics itself. Asteroids don't produce their own light. We only see them by the sunlight they reflect, and dark, carbon-rich asteroids reflect almost none of it. An object could be moving directly toward Earth's general neighborhood right now and simply be too dim, too small, or too close to the glare of the sun for any telescope on the ground to notice. Which is exactly why NASA is building something that doesn't look for reflected light at all. So here's what NASA is actually building to fix that blind spot. It's called NEO Surveyor, and it represents the first time in history that a space telescope has been purpose-built from the ground up for a single mission. Find the asteroids that could hurt us before they arrive. Instead of visible light, NEO Surveyor is designed to detect infrared heat. Every asteroid, no matter how dark or how dim invisible light, absorbs sunlight and re-radiates that energy as heat. To an infrared detector, even the darkest, most reflective-resistant asteroid in the solar system glows. This single design choice solves the exact blind spot that let the Chelyabinsk object slip through undetected in 2013. The telescope will be stationed not in orbit around Earth, but nearly 1.5 million kilometers away, at a gravitationally stable point called L1, giving it a clear, uninterrupted view of the regions of sky closest to the Sun, the same regions where our current ground-based system is functionally blind. Once operational, NEO Surveyor is expected to run a 5-year survey designed to find at least 2/3 of all remaining undiscovered near-Earth objects 140 meters and larger. After nearly 2 decades of missed deadlines, budget delays, and a mission cost that grew from roughly $1 billion to $1.6 billion, NEO Surveyor is now targeting a launch no earlier than late 2027. Almost nobody outside the space community is talking about the twist buried in that timeline. This mission has already slipped past its original deadline once. It was supposed to launch by 2026. It didn't. The gap between the moment we decide an asteroid detection telescope is necessary and the moment it is actually collecting data in space is measured not in months, but in years, sometimes decades. Every year that gap remains open is another year that unknown objects continue moving through the dark, unwatched. But finding an asteroid is only half of the problem. The other half is far stranger and far more dangerous. What do you actually do if you find one that's coming? For most of human history, the honest answer to that question was nothing. There was no plan. There was no technology. If a large object had been discovered on a collision course with Earth at any point before the 21st century, the correct response would have been evacuation, not deflection, because deflection had never been attempted. That changed on September 26, 2022. NASA had spent years designing and building a spacecraft with one job, and one job only: fly, unmanned, directly into an asteroid at roughly 22,500 kilometers per hour, and see what happens. The target was not a threat to Earth. It was a small moon called Dimorphos, orbiting a larger asteroid called Didymos, roughly 11 million kilometers away. Scientists chose it precisely because a controlled experiment needed a safe, harmless test subject. The mission was called DART, the Double Asteroid Redirection Test, and what it attempted had never been done in the entire history of our species: deliberately slam a spacecraft into an asteroid, on purpose, to see if we could physically change where it goes. At mission control, the final images streaming back from the spacecraft's camera showed Dimorphos growing larger and larger in the frame, boulders and surface texture becoming visible in the spacecraft's final seconds. And then nothing. Signal lost. Impact confirmed. Impact. Now came the wait. Not the 44-hour round-trip communication delay of a distant probe, but weeks of careful telescope observation from Earth, measuring the exact rhythm of Dimorphos orbiting its larger companion, watching for any change in that rhythm at all. The result, when it came, was not subtle. Before impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After a single spacecraft, weighing about as much as a golf cart, struck it at high speed, that orbital period shortened by roughly 32 minutes. 32 minutes from one impact, on a target millions of kilometers away. It was the first time in human history that our species had deliberately and measurably altered the motion of a celestial body. Not with explosives, not with force applied at the moment of arrival. With physics, momentum, and years of precise planning delivered from hundreds of millions of dollars, spacecraft the size of a vending machine. This is not a footnote. This is not a minor technical success buried in a research paper. This is proof, real, measured, repeatable proof, that if we find a dangerous asteroid early enough, we now know how to nudge it off course. But here's the detail that should temper any sense of easy relief. Early enough is doing an enormous amount of work in that sentence. This is where the story stops being hypothetical. In late 2004, astronomers discovered an asteroid roughly 340 meters wide, later named Apophis, after the ancient Egyptian god of chaos and destruction. Early orbital calculations suggested something that had never been calculated before: A real, non-trivial chance, at one point estimated near 3%, that this asteroid could strike Earth in 2029. A 340-meter object impacting Earth would not be a regional catastrophe. It would be a continental one, with energy in the range of tens of thousands of megatons. For a brief period, Apophis was the most dangerous known object in the solar system, and scientists at NASA and observatories around the world scrambled to gather more observations, refine the orbit, and determine whether the 2029 impact scenario was real. It wasn't. As more precise tracking data came in, the impact probability collapsed toward zero, and by 2021, NASA formally ruled out any risk of impact from Apophis for at least the next 100 years. But Apophis did not stop being interesting. It became something else entirely, an opportunity. On April 13th, 2029, Apophis will pass within roughly 32,000 kilometers of Earth's surface, closer than many of our own communication satellites in geostationary orbit. It will be the closest approach of an object this large in recorded history, visible to the naked eye without a telescope across parts of Europe, Africa, and Asia. And waiting for it will be a NASA spacecraft that has already done this once before. OSIRIS-APEX, the same spacecraft that spent years orbiting the asteroid Bennu and successfully returned a physical sample of it to Earth in 2023, has been redirected toward Apophis. About an hour after the 2029 close approach, OSIRIS-APEX will use Earth's own gravity as a slingshot to catch up to the asteroid, arriving within weeks to begin an 18-month campaign of close observation. This matters far beyond scientific curiosity, and here's why. When Apophis swings this close to Earth, our planet's gravity will physically stress and reshape it, potentially triggering landslides, surface shifts, or changes in how the asteroid spins. Scientists will be watching in real time to see exactly how a solid, rocky body responds to a close planetary encounter. Data that directly informs how future deflection missions, whether kinetic impactors like DART or more exotic tools like a gravity tractor, would actually need to be designed and timed. We are, in effect, being handed a natural experiment that we could never ethically engineer ourselves, an asteroid the size of 3 football fields, sweeping past our planet close enough to touch our satellite shells, and a spacecraft already positioned to learn everything it can from the encounter. Now let's come back to why any of this should matter to someone who is never going to work at NASA, never going to build a telescope, and will likely never see an asteroid with their own eyes. Because the uncomfortable truth sitting underneath all of this is simple. Planetary defense is not a solved problem. It is a race that is currently being run in slow motion against an opponent that has no schedule, no warning system of its own, and no obligation to announce itself before it arrives. We have found less than half of the city-destroying asteroids large enough to matter. Our most powerful dedicated detection tool, NEO Surveyor, is still years from launch, after already slipping past one deadline. Our only proven deflection method has been tested exactly once, on a target chosen specifically because it posed no risk if anything went wrong. And the object that gave humanity its biggest scare in living memory, Apophis, only stopped being a threat because we got lucky enough to refine its orbit in time, not because our detection system caught it early with room to spare. If a genuinely dangerous, undiscovered asteroid were found today with only a few years of warning instead of decades, the honest answer is that our options would be limited, untested at that scale, and entirely dependent on exactly how much lead time we had. Every year of advance warning is not a luxury. It is the single variable that determines whether deflection is even possible at all, because changing an orbit by a small amount, applied early, compounds into a massive difference in position by the time the object would have reached Earth. Applied too late, even a direct hit with everything we have would not be enough. That's the actual state of planetary defense in 2026. Not a finished shield, not a solved problem. A system still being built, one budget cycle, one delayed launch, and one hard-won discovery at a time, racing against objects that have been quietly crossing our orbit for 4.5 billion years before any of us were here to notice. Here's what I want you to take away from all of this, because there's a fact sitting in the middle of this story that's easy to miss when you're focused on the telescopes and the spacecraft and the physics. We are the first generation in the entire history of our species that has both the ability to see this threat coming and the technology to actually do something about it. Every human being who ever lived before, roughly the last few decades, faced exactly the same cosmic shooting gallery we do. The same undiscovered rocks, the same silent orbits crossing our own, with absolutely no way to detect them, track them, or move them. They lived with a risk they could not see. We live with a risk we are only just beginning to see clearly, and for the first time, we have a tool, proven in 2022 on Dimorphos, that says we are not helpless against it. The dinosaurs had no telescopes, they had no space agency, they had no warning at all. We have a global tracking network, a spacecraft that has already nudged an asteroid off course, and a purpose-built infrared telescope racing toward a 2027 launch specifically designed to close the gap in what we can see. What we don't yet have is certainty that we'll finish the job in time. That part is still being written quietly, underfunded, delayed, in observatories and mission control rooms most people will never think about. By scientists who understand something the rest of us mostly don't. The sky is not calm and empty. It is moving constantly. And something out there already has our name written into its orbit. We just haven't found it yet. The question is whether we find it before it finds us. If this kind of story is what you come here for, subscribe and turn on notifications, because we're going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video and share this with someone who needs to hear it, because this story deserves more attention than the silence it's getting. Thanks for watching.